okay, which is physics informed. Yeah, physics informed loss functions. This is the second chapter. So the second method, if you want, to try to incorporate physics priors. So again, let's restart from our high-level view. 3 different categories. We're of course looking at the third one now. You may ask, why don't we go in order? Yeah, why don't we do physics encoded first? Well, that's because I would like to keep it for the final part of the day, and then tomorrow, because it's actually the biggest chapter, the physics encoded one. It's the one in which we have many approaches, actually. So I would like to spend more time on that. So let me first jump to physics informed, in which indeed we act on the loss function. So there we don't want to simply have data in our loss function, but we want also to have some physics information, inside. And the physics information tells us that we want to satisfy some governing equations, which we may have beforehand. Indeed, so just from a very high level view, what do we do actually in physics informed machine learning, which by the way is a very popular term? Well, basically, yes, we want the loss function to incorporate some soft constraints, and these soft constraints basically encode the physical equations. So here, as we said before, we can have some ODEs or PDEs, so ordinary differential equations or partial differential equations, or boundary conditions, or physical models, whatever, that we incorporate in the loss function. And the loss function is typically quadratic, yeah, so this is something we don't want to typically spoil. We want to still have a quadratic loss function because it's good for numerical convergence. And again, yeah, this is the paper, the survey paper that we always refer to, in which they also talk about physics-informed models. So here, indeed, the motivation is, on the one hand, and this is the most popular probably approach, to learn to solve to learn the solutions of how to solve mathematical equations, like partial differential equations, which are very complex to solve analytically, or impossible to solve analytically in most of the cases. We need tailored solvers, like finite element methods or numerical solvers, which take a lot of time to compute. And so we want to use neural networks to speed up the solution. This is one motivation. Second motivation is actually not to solve complex equations, but rather combining imperfect models, which we may have, physical models, with data. Okay, so sometimes we have little data, but we have some model, and then we can combine two in the loss function, and this is something we're going to see. And this is something we do to improve basically the generalization of our database neural network outside of its domain. Okay, but we will get there. Yeah, so here I would like to start from probably one of the most well-known papers in the field of physics-informed machine learning, which is this one you find here by Raisi, 2018, Physics-Informed Neural Networks, a deep learning framework for solving forward and inverse problems involving nonlinear partial differential equations. This is a very well-known paper, super cited, yeah, like thousands of citations. And that's indeed a seminal paper, because what they did was basically proposing neural networks to solve or to discover new partial differential equations to solve specific problems, of course, yeah, yes. And basically they start from a very general nonlinear partial differential equation, which you may write in this form, where you have the u that is in general the unknown solution that you want to find, and note that u depends on both time and so time t, and also another state or another variable x. Okay, so it's actually not only dependent on t, which is probably the most common case, okay, for you in your research maybe, but in complex problems, it may be that the u depends also on x, another variable. And then u of t is the partial derivative with respect to time of u. And lambda can be known or unknown parameters, depending on the use case. And these parameters appear inside the nonlinear operator n, which is in general a nonlinear operator, whatever. Okay, so a very general form of a nonlinear PDE, partial differential equation. And this includes a lot of physical phenomena, by the way. Oh, yeah, and by the way, maybe I forgot to say, remember to write your name in the Excel sheet, yeah, for the presence. Yeah. And the slides are also available on the Google Drive folder. But yeah, coming back here, so this includes a lot of physical phenomena. This PDE, you can model diffusion processes, for example, fluid dynamics. But more in general, any ordinary differential equation is of course contained in a set of partial differential equations. So it's a special case. So this category is actually quite broad. Okay. And now we can have two questions. Yeah. First question can be how to, okay, given lambda, so if the neural operator is fully known, lambda is known, how to find a solution, how can a neural network learn a solution U to satisfy the nonlinear PDE? So how can a neural network learn its solution given the parameters? And the second question is instead, what is the best lambda, okay, to fit our experimental data? And the second question is what they call discovery of PDEs. So they basically want to identify their parameters, which still for a PDE is not a tricky task, yeah. It's not a trivial task. But here we would like to look deeper, especially in the first approach, which is given lambda, indeed find a solution of a PDE using neural networks. Okay, questions here? Is it clear? Yeah. Indeed. So let's have a look in detail about question 1. So let's restart from our PDE. We put it there. And simply one can say, okay, this is my PDE. So basically I want to have the left-hand side, which I can call F. I want it to be as close to 0 as possible, right? Because I want it to be equal to 0 in the best case. So I want to basically have it as close to 0 as possible. And indeed, and our goal is to learn the solution U using a neural network. And what they propose in this paper is to use a tailored loss function, yeah, so physics-informed loss function, in which they have basically two components. Okay, we can have more than two, but in this case they have two. So one of the components is called MSCU, and MSC stands for mean square error. Okay, so we want to basically minimize then this loss function. Okay, so minimize the mean square error, which consists of two parts. The first part, MSCU, is basically imposing or inviting the solver to find a solution that is close to the initial conditions that we want to satisfy. Okay, yeah, to the boundary conditions or initial conditions that we can have.
So yeah, what can help is to think that you are working in a space, no? So you decide your space of solution. Okay. So commonly in this example, if I don't make a mistake, you have X as a variable, and then you have the time that are the two variables that you have. And now we are imposing the solution here because these are given. Okay.
Yes. So the boundaries can be given. Yeah, we want to learn the solution inside our domain, but the boundaries could be given, or at least some points along the boundaries. Exactly. At some points along the boundary could be given. And so in this case, this UI, this is something known. So the solution at certain points I is known. Okay, we can have a certain number of boundary conditions that we want to impose. Okay, so we don't want to learn everything, but something is known, of course. And then the second part, the MSCF, is instead the most interesting part, because this is simply penalizing the violations of the governing PDE. Okay, so we have our F, which is the left-hand side of the PDE. Here we're simply saying, please minimize the square norm of F So please minimize, please have, if you want, f as close as possible to 0, right? So minimizing f squared means I want f to be as close to 0 as possible. And this means implicitly penalizing the violations of the PDE, okay, of the governing equation. And this is a very powerful means that we have to learn solutions. So we don't need data here, by the way. So we don't have, the only data we have is here, this UI. This is the only, yeah.
That are here.
Exactly, so the domain, the boundaries, yeah, the boundaries of the domain. This is the only thing we give from the outside. And then all the rest is learned from the equations, okay? So the neural network learns actually to solve this complex equation.
Yeah, and the other
Yes.
points here, okay, you see T, F, and XF are generated randomly inside the domain.
Yes.
Here,
Yes.
like this. And in those nodes, you try to minimize and verify the governing equation.
Yes.
Okay.
So these are also called commonly collocation points. And
Yeah,
they also called collocation points. So you define their position, where you want to place them inside the domain, yeah. And then you want to enforce the satisfaction of your PDE in these points that you define inside the domain. Okay, and this is indeed a very powerful tool, and it's what we call, it's what they call the physics-informed neural networks. And nowadays, everybody's talking about, of course, physics-informed neural networks.
It was the first one.
It was the first one, yes.
To try to include
physics.
And from that paper, everybody started to talk about informed physics.
Yes.
But
yeah.
Then, I mean, the community now started to maybe give some more more insight, more precise definition
of what is
informed guide.
But still, this is indeed, this was the original paper, and there are many others derived from this one. And so some remarks, yeah. So here, by the way, U is approximated with the neural network. But of course, we don't care about the internal architecture. So here, also in the paper by Raisi, they used a very general purpose neural network. So what we called yesterday multi-layer perceptron, or it can be a recurrent neural network, but very general purpose. Yeah, no physics inside the architecture. Also, there's no guarantee that we're going to solve the PDE, right? So it's just a gradient descent algorithm in which we want to penalize the violations of the PDE. But there's no guarantee that we find the exact solution. Okay, we may also converge to a bad local minimum, no guarantee. But in practice, it turns out that if the PDE is well posed, so at least if the solution is unique, which happens maybe for many physical systems, then a sufficiently deep neural network, so with many hidden layers, can approximate its solution quite well, yeah, in practice.
So it's a trade-off. If you go back to the here is a trade-off of these two minimization.
Yeah.
So depends how you penalize these with respect to these. Of course, you get maybe a good matching of the boundary, maybe less good inside, or the opposite. No. So
yes. So yeah.
Is there any study that correlates the deepness of the networks and the type of partial differential equation, or?
Yeah, good question. Yeah, so David asked if there is a correlation between the depth of a neural network and the fact that we can solve actually a PDE or not. I think this is still an open question, but if you look at these papers, they tend to say that they found also not only for this paper, also in other ones, they say that okay, they are just using a sufficiently deep model, so a model that is really actually with quite a lot of neurons and layers, hidden layers, even though they typically don't show ablations for that because it's not the purpose probably. But they typically say we use the sufficiently deep model. So implicitly, this means if the network is shallow, so it's not deep enough, the approach doesn't work. Yeah. So you need sufficient complexity to accommodate all the variability that you need to solve the equation.
Okay.
But I think this is an open question, yeah. So it would be a promising direction actually to look into.
In theory, two layers.
Yeah.
Yes, exactly. Yeah, in principle, yeah, you have the universal approximation theorem, and actually one layer one layer would be enough.
Hidden and one.
But then you have to have a lot of neurons. On the other hand, okay, this is also something that the community is not really able to explain, why having deep models is better than having a one single layer but with many neurons. Okay, these are two alternatives, right? Either you use a multi-layer perceptron with a lot of layers, a lot of hidden layers, or you use a one hidden layer but with a lot of neurons inside. These are two alternatives. The community tends to prefer the first approach, so deep neural networks, at least for certain applications, including this one. But nobody's really able to explain why that works. Of course, if you have more layers, you have more nonlinearities because you have more activation functions. You can also use different activation functions for each layer, and then you have the capability to model more nonlinear systems intuitively. Like the first layer could have a tanh activation, the second layer could have a rectified linear unit, so on. And then by combining them, you can model better the nonlinearities. But these are open questions. Yeah,
I think it's also because you create some hierarchy inside the network itself.
Yes, exactly.
So it's some neurons inside the networks are delegated to do some stuff.
Exactly. Yes.
Function.
Yeah.
So maybe that's because.
Exactly. Yeah, good point. Yeah. So yeah, it can also be that some neurons then specialize implicitly on learning some parts of the dynamics. Yes. But yeah, so in general, yeah, so here in general you can have some weights, yeah, to weigh the two objectives. Okay, so you can prefer to stick to your initial boundary conditions to satisfy them better than the dynamics, or vice versa. It's always a trade-off, yeah. And indeed, so we said no guarantee, but in practice it works. And then, yes, at least for the use cases of this paper, there they had the problem that solving these PDEs was taking a lot of time. So once the neural network is trained, you just need to evaluate it. It takes a fraction of a millisecond. So it's way faster, while solving the PDE numerically may take hours, yeah, if it's a complex problem. So in their case, this was also an advantage. And then indeed, there's an extended approach. So building on top of this model, on top of this idea, people then started to say, okay, but then what if we don't have just physics, but we also have more data? So not only the boundary data, but we also have some data inside the domain. Then in this case, we can really, it's what, according to me, really has a potential, which is combining data and physics in the loss function. And this is something we're going to see later in the examples. Is really powerful because you can maybe make the most of both approaches. Okay, so you can extend the generalization of your model, especially in regions where you don't have data. Okay, but this is something, again, we're going to see later. Yeah, so questions here?
Just a comment. About, so there is actually theory as to why having a deeper neural network is, like, in quotes, better. Basically, like, as you stack layers, you gain exponential expressivity. But if you just add a bunch of neurons in the same layer, it's like linear. So adding depth increases expressivity exponentially, so you get closer to like a general function.
Yeah, indeed. Yeah, good point. Yeah, thanks for mentioning that. Indeed. So maybe you know that part of the literature better, and maybe yes, there are some studies that explain why in deep models perform better, at least on specific tasks, than single layer models. Yeah, thanks for pointing it out.
Is another point that was a demonstration that I was looking to find the paper that is related to the sparsivity. So when is not a matter only of the layers, but it is matter only of the structure. The structure matter because is reduce the connectivity between layers, and these make more the network more sparse. So the connection between layers are more sparse. And there is a demonstration that I'm not looking. I'm looking for find it, and it say that when the network the connection are sparse, you get a better performance. And this is probably a reason why, for example, convolutional neural networks or transformers that have a very specific shape of layer that is not a fully connected layer, because in principle a fully connected layer can mimic a transformer, can mimic a convolutional network, no, in theory. But when you have a multi-layer, it's better to have a structured connection, so you reduce the connection. That is improving the fitting. But yeah, if I find the reference, I will show you. Yeah.
Okay. Yeah.
Okay.
Good points. Yes. Yes, indeed. So these are somehow open topics, but what I wanted to say is that, okay, maybe there are methodological papers that explain you why one approach is better than the other, but then if you look at application-oriented papers, they simply say, okay, in our case, it worked better in one way or the other, and not always they find, let's say, rigorous solutions or rigorous motivations. Yeah, so if there is no other question. Oh, yeah, yes.
Have you tried to use Kolmogorov-Arnold networks?
Yeah. This is a good point. Yeah, Kolmogorov-Arnold is a special type of networks that probably we're going to see very briefly tomorrow. But it's a type of neural operator, so people also use that. There is also some variants, physics-informed Kolmogorov-Arnold operators. It's something very technical, so there they have their own universal approximation theorem. They have their own, so it's totally different from multi-layer perceptrons, for example. But we may see something about that tomorrow. Yes. But thanks for the question. Yeah, indeed. So if there's no other question, we can start having a look into the applications of physics-informed neural networks or physics-informed learning. And indeed, some applications are about physical systems, you see here, some others are about robotics. We have a lot in the community. Okay, let's start closer to Raisi's paper. Actually, this application is in the paper by Raisi, which is again related to the solution of partial differential equations. And it's a complex one in this case. Yeah, it's a very complex equation, which is the Schrödinger equation, which basically you can use to model a lot of physical tasks, including wave propagation and a lot more. And the challenge here is that you see there the PDE, it's nonlinear, it's actually complex. This is the imaginary number. It's complex, there are absolute values. It's a nonlinear PDE with periodic boundary conditions. So we know, for example, in this case, we know, okay, so this is the equation, and these are the boundary conditions. So we know the solution at time t equal to 0, and for any x, this is the form. 2 times this hyperbolic secant of x. And then we know that for x equal -5, the solution is equal to the one that it has at x equal +5. Okay, and the same for the derivative. Same for the derivative with respect to x. At x equal 5, it's equal to the one at x equal -5. So we have boundary conditions that are cyclic, periodic. Indeed, the equation is defined only between -5 and 5, and t from 0 to pi half. But solving this is extremely tricky. Yeah, even numerically, it's super tricky. And it's indeed a complex valued solution. So so h, you can express it as u and v, where u is the real part and v is the imaginary part. And okay, in this paper, they proposed to use a 5-layer neural network. Okay, even here, they didn't say why. They just said it works. It's sufficiently complex to encode to actually contain all the complexity we need to solve the equation. again, it's a two variable. So h depends on time and x, so it's a partial differential equation. Again, yeah, just let's apply what we learned before. So we call f the left-hand side. Okay, f is simply the left-hand side that you find here. And your goal is to drive f to 0, right? Ideally, in the loss function, you would like to bring f as close to 0 as possible. In this case, we have 3 terms, but it's the same as before. So the first term imposes the satisfaction of the initial conditions. In this case, at time 0, at time t0 equals 0, we have a certain shape, okay, which is this one, 2 times the hyperbolic second of x. So we know along time t equal to 0. Yeah, exactly. Yeah. So along time t equal to 0, we know the solution. This is given to us for free. Yes. And of course, you don't want to forget it. Yeah, you want to encode it in the loss function. And then the second term is enforcing the periodic boundary conditions. Yeah, so for x equal to 5 and minus 5, yeah.
The boundary, you know.
Yeah, exactly. So exactly for every time t. Exactly. For every time t and x equal plus 5 and minus 5, we don't know the solution there, but we know we have periodic conditions. So from there, everything starts again. Okay, so in terms of the solution and also partial derivative with respect to x. And this is something you can easily incorporate in the loss function. You see here we have indeed the first term is for the value of h. The second term is for the derivative of h with respect to x. And again, we're penalizing quadratically both terms. We're summing them. And NB, okay, this NB is the number of points in which we want to enforce the conditions, yeah? So here we can have some discretization, and we want to enforce the periodic boundaries on a certain number of points.
You sample.
Yeah, we sample them, yes, exactly. Okay, and then the last term is, of course, the physics-informed term, yeah, the really physics-informed term, which is the Schrödinger equation. Yeah, so we take the Schrödinger equation, the left-hand side, written like that. We put it quadratically in the loss function. Okay, so we put the square norm of f in the loss function.
I think here there is the, I mean, the something that was new in the field of neural networks, because in all the other terms, H is a network, no? So you run the network, you get the output of the network, and you compare to minimize some loss, and this is standard. What was new, I think, for the field of neural network was to use the gradient as an output of the network. So you have the network, you can, using automatic differentiation inside the tool, was PyTorch, if I remember well, in the paper, you can derive your network with respect to t, that is an input of the network, okay? So if you ask to PyTorch to compute the gradient of a specific input of your network, you get an output, a numeric output, okay? So here was computing the derivative of the network with respect to the time, the derivative of the network 2 times. So you get the output of the network, and then again, you derivate the second time with respect to x. And here is just computing h squared. Okay, so this was new. So what was new as regarding the field of network was to use the gradient of the network as an output of the network. Okay, so this, I think, was something really, really new in the field.
Yes.
Yeah, please.
Is the gradient computed with the forward mode, right?
Yeah, you compute the forward, and then you make a gradient of your network with respect to the input, and you get another output that's still differentiable, and blah, 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 and you can compute those terms, this term in particular. Okay. Yeah.
Yes.
So the loss function is computed on the gradient of the network, not on the output of the network.
Yeah.
So
basically to evaluate our loss, to evaluate our loss, we need to also take the derivatives of our neural network with respect to time and age.
Yeah.
And indeed, this is something that you can also do analytically, but it can explode easily.
Yeah.
So people use automatic differentiation. Okay, in this course, we're not looking in detail into automatic differentiation, but it's a numerical technique, or it's a technique to compute derivatives using the chain rule, basically. So as you do when you basically compute derivatives by hand, more or less, you use a chain rule to compute them. And similarly, they use a chain rule to compute derivatives of very long functions without having analytical expressions that can explode. Okay, yes.
Sorry, I don't understand what is being minimized in the F term.
Okay.
Doesn't look like, an
Yes.
error.
It looks, sorry?
It doesn't look like an error to me.
Yeah, like an error.
Yeah.
Okay. Yeah, so in this, yeah, good question. So indeed, F in this case is the left-hand side, right, of the equation. And this equation you would like to be equal to 0, right? So we just take the F, we just rename F as the left-hand side of the equation.
You impose.
Exactly, but
You are
since we would
minimizing,
yeah.
Because I didn't notice
Yeah.
it was equal to 0.
Exactly, yeah, because here we would like this term to be equal to 0. So you're right, it's not an error term. It's not the classical error term in which you have something and then something, so something unknown and something known.
Target, you have the target and the
Yes,
output of the network.
exactly.
Here, the target, I mean, the target can be 0.
Yes, so ideally, exactly. Here you can write F minus 0 norm squared, yeah. Exactly, so you would like to derive F as close as possible to 0 because that's what your equation imposes, yeah, basically. Yes. Is it more clear now?
Yeah, yeah.
Okay, great, yeah. But thanks for the question, yeah, indeed. Okay, and yeah, so indeed, we can have different terms in the loss function. And once again, different terms means also different weights. So here you don't see the weights, but in principle, you have one weight in front of each term, and then you need to manually tune the weights. Yeah, that's, of course, part of every optimization problem with multiple objectives. Yeah, okay, so this is the loss function. The thing is, yeah, once again, we don't need, for this term, we don't need ground truth, yeah, as we said now. We just need the equation itself, F. The form of the equation is known in this case, but we don't need ground truth data inside the domain.
Yeah, this is very interesting because you can still,
Yes.
to refining the solution, you can still generate hundreds of thousand points inside the domain, and you can improve the quality of the of the solution that you find inside the domain. Okay.
Yeah, so basically we don't need ground truth data inside the domain, only the initial conditions and the periodic boundaries. Yeah, so this is powerful. Yeah, we don't need to collect data, which is of course tricky, can be tricky in real life. And this is, yeah, this is exactly this plot. Yeah, yeah. So the plot we were drawing on the blackboard is this one. So we have basically that h. Okay, this is the absolute value of h, but you can think of h. This is the x coordinate. This is the time coordinates, and this can be your the points that you sample. Okay, these x's can represent the collocation points that are actually inside the domain, or they can be the ones on the boundary. Okay, I don't remember in this case. But basically, you can sample some points inside the domain to impose where you want to satisfy your equations.
And in the tree plot below, you have the solution in the tree dashed line there.
Yes, indeed. So this one is the solution for time t equal to 0.59 seconds. And you see there is actually a quite good matching between the exact solution computed numerically, taking a lot of time, and the neural solution computed basically with a very low inference time. Yeah, and also for other time instants, you have a good approximation. Yeah.
Of course, this solution works is not generalizing for any initial condition.
Yes.
Okay, this is important to understand. So, of course, if you change the initial condition of the boundary, the solution is completely different and you need to throw away your network.
Yes, yeah, indeed, good point. Yeah. So here it's just solving the problem for this setting in which we have certain boundary conditions. If you change them, you need to do everything from scratch. Yeah, the solution is gone and you need to retrain everything. Yes. At least
really
in
find a solution, analytical solution, analytical of a general case, but is the specific issue.
Indeed. I mean, this is the standard approach. And then there are approaches that, I mean, one can extend this approach to actually make it more general, to learn actually a solution that depends on the boundary conditions without retraining every time. But this is something we can do, I mean, as researchers, but the original approach was not doing that, yeah? And okay, so other questions on this example, also from online, of course. Otherwise, we can have a look at the next example, which is still very related. I just wanted to present two examples. So here we have a soft robot finger, okay, which you see here, and it's actually a pneumatic finger. Yeah, so by pumping air inside, you can change the shape of the finger. You can move the finger. Okay, so you can be
you can think that the finger is made like this.
Yes, exactly. So there are some
here is getting hair, and when getting hair, this is increase the shape, and the finger is turning. And
yes, exactly. Yeah. So you can basically change the shape of the finger by pushing air inside. And the thing is, this is a soft robot, if you want. So it's a robot that can deform itself. So it's not a rigid body. And here, to solve this type of problem, to compute the deformation of the finger as a function of its internal pressure, in principle, you need to solve continuum mechanics partial differential equations, Navier-Cauchy model. Again, partial differential equations, no analytical solution probably exists, or unless in some very specific cases, yeah. So basically here you want to compute the deformations along X and Y, so the two axes, Z is the vertical axis, X is the horizontal. So you want to compute Ux and Uz using these two equations, where Fx and Fz are the unit forces per unit volume caused by gravity, okay, due to the gravity. And again, so what can we do? Okay, let's use a neural network to learn Ux and Uz. And in the loss function, again, we have two terms. First term is imposing initial conditions. Okay, so again, these Uxi and Uzi is known. Okay, we can enforce it in the loss function. And the second term is imposing the satisfaction of the Navier-Cauchy model of both equations. Yeah, in this case, we have two equations. So what can we do? We can simply sum. The violation of the first equation plus the violation of the second equation. And again, these endpoints is something that you can choose inside the domain. You can sample the domain as you wish and impose the satisfaction of the equations inside the domain.
I want to stress the fact that here was called physics guided.
Exactly, yeah, good point. So here, if you look at the title of this paper, it was actually called Physics Guided Deep Learning. So there is confusion in the community. Yeah, once again, some people call it physics guided, some people physics informed.
Yeah, so you do not rely on the title to understand what is it.
So in this course,
now we try to give a little of clarification on that. But yeah, so please have a look. When you want to understand what is the approach, it's better to have a look inside to understand really what is doing.
Yeah. So indeed, there is a confusion in the community. people mess up the terms, but we want to also give a unified taxonomy, at least for this course and at least for the future, hopefully. Yeah. Right.
Do you remember
Yeah.
what was the meaning of the meaning, the value of lambda and
mu? I think they are known values. Yeah. I'm not sure, but I think they are parameters that you can have fixed. Yeah. So basically, what they are doing here is that they are using a very general purpose neural network here with hidden layers. They want to estimate ux, uz. Okay, these are the outputs. The inputs are the point on the domain, so the x coordinate, the z coordinate, so where you are inside the domain, and also the pressure. P is an additional input. The applied air pressure, and then the network computes ux, uz, and then you use this loss function, which we've seen before.
You derive the network.
You take
I think it's clear. Of course, this process is given by the computation of the gradient backward. No? So you get the derivatives.
So basically, we compute the derivatives with automatic differentiation once again, because we need to differentiate this neural network in principle with respect to the inputs. And then we encode everything in the loss function. All the derivatives then appear in the loss function. And the loss function, and then we want to minimize, of course, this loss function and train the parameters of this neural network to minimize the loss function. Yeah. And by doing so, we are finding solutions of the differential equation or the PDE. Okay, so then they use the Adam optimizer, okay, which is a gradient-based optimizer to do everything. Yeah, basically. And they were benchmarking against numerical PDE solvers. Yeah, in this case, they had to use finite element analysis. Yeah, with ANSYS. Yeah, which is a popular software tool to solve finite element problems. But with ANSYS, I mean, you need to do everything by hand. You need to write code. You need to solve it. Takes time. They were actually showing that the trained PIN, physics-informed neural network, is quite fast. I mean, once it's trained, you can solve the problem in real time. And for different pressures, okay, for different values of the pressure, you have different solutions. So, okay, from 50 to 10 kilopascal, you change the form, the shape of the finger, but you're still able to approximate it quite well. So the pressure here is an input, okay, for the model. So if you change the pressure, the model should be able to generalize theory if it's trained well. If you change the pressure, you can then approximate the shape of the finger. Okay, and this is the comparison with the finite element. Yeah, very complex, of course. Questions here? Yeah, we can maybe already take 10 minutes break, and then we restart at 10:15. And we just close then the final examples of physics informed, and then we move on to physics encoded. Okay, good. To restart by maybe following up on what we were saying before.
Yeah, I mean, is a work on nature science communication that I like the fact that we argued that the contrary to general purpose artificial intelligence should not have a fully connected layers. So taking inspiration from biology, say that in the sparse connectivity can improve the performance of the network in general, and they make some example. They may be a little bit mathematics. I mean, there is a lot of mathematics behind, but the idea is give a structure. So I mean, the takeoff message for me was give a structure to the network, reduce the number of connection, okay, instead to have a fully connected layers. And for this reason, you can improve the quality of the fitting. Okay, so is I think one of the motivation behind, for example, convolutional or transformers are working well. I mean, they have a specific structure, but still they are creating a not fully connected connection between layers. So this is one interesting point. We give you this paper.
Yeah, I just put the link in the chat. Yeah, it was just to follow up on what you were saying before, like depth of the network, whatever. Yes, yeah. We just put the link in the chat.
Of sparsivity, if you look online, that say mostly the same things.
Yes, and by the way, we're going to discuss more on that topic, internal connections, when we talk about physics encoded architectures. So we can continue from what we left before. So physics informed neural networks. And okay, up to now, we learned that physics informed networks can learn to solve complex partial differential equations. But then you might ask yourself, okay, but in my research, I'm not dealing with the PDEs, so I don't care about physics-informed neural networks, right? But actually, no, you should care, even if you're not dealing with PDEs, even if you have whatever other physical system, because they are actually useful, even beyond PDEs, because if you think ordinary differential equations are a subtype of partial differential equations, and with ordinary differential equations, you can describe the dynamics of a drone, you can describe the dynamics of whatever other system. So in this case, they are learning the dynamics, the authors of this paper are learning the dynamics of this drone, okay, of this quadrotor. And the dynamics is, can be very complex. You have states, x, y, z, you have velocities, you have angular velocities, you have angular accelerations. So this can be a physics-based model described with the Newton equations. But you can still write it in this form, similarly to what we did basically before. So you can still write it in the form partial derivative of y, where y is the collection of all the states of your model, plus a neural operator equal to 0. Okay, this is can still be written like that. And then same as before, just write the left-hand side of the equation in this form, collect it in the variable L, and then learn the solution with a neural network. And this is exactly what they did. So learn the solution y hat, which is the collection of all the states using a neural network. And it's pretty simple. So we have a loss function here. Again, two terms. First term is imposing, actually, it's not the same as before, sorry. Here we have a loss function that is still composed of two terms, but the meaning is different from what we were describing before. So it's not boundary conditions plus equations, plus violation of the equations. In this case, we're doing something different because we have a physical system, right? So we don't have PDEs to solve. We have ODEs to solve, but we also have real data, maybe with our drone, right? We drive our drone, we collect data. How can we combine the data plus the physics together? Okay, this is what they do here. So the first term here, MSCY, is the mean square error between your model predictions, y hat, and the ground truth data, right? So this is supervised learning with collected data hat y ref. This is data you collect by driving the drone. And you put it in the loss function. This is quite standard, supervised learning. But then they have a plus, okay, and here NT is the number of data samples you can collect, and Y is the number of outputs, okay, which is the number of states in your model. MSCL, so the second term is the physics loss. Okay, so here you want to penalize the violations of your physics equations. Okay, the ones we've seen before, so these equations. So basically you have one part of the loss that is data-based, the other part that is physics-based. Okay, and this is very powerful, Actually, quite few people do that, but I would definitely recommend also for you to consider this approach, because okay, in this case, in the physics loss, we have NL as always, which is the number of collocation points that we choose if you want inside our domain to impose the physics loss. And gamma is a weight in this case that weighs data versus physics. So if gamma is high, it means we trust a lot our physics model. If gamma is low, we trust more the data. Okay. And in principle, one can say, okay, inside my domain, I have data, I have physics equations, I combine them both together. Okay. Okay, yes, and in this case, they were showing that they could outperform actually with this approach an extended Kalman filter to estimate some parameters of their drone. So the dynamics plus some parameters maybe. Actually, the Kalman filter was taking some of the parameter as known, okay, while their model was learning everything, no known parameters. Yes, and they had some metrics they were showing they could actually outperform the prediction of the Kalman filter. But the real power here, what I was saying before, is indeed the combination of data plus physics. And let's consider this case. This is really something important for physical systems, robotics, whatever. Is the combination of data plus physics as a regularization term. So indeed, we have a data loss and a physics loss. And this is effective when we have real data, not in all the okay, we can have real data in the whole domain. That's the ideal case. But most of the times we have the data in a portion of the domain, right? So a portion of the domain we have data, and there we have our data loss, right? Where we have data. But real case is we have the data in a small region of the domain, but we also have an imperfect model that we can use, an imperfect physics model. And then what we do, we can impose the data loss where we have the data and the physics loss in the data sparse regions. So where we have little real world data. And this is powerful because in this way, you can literally separate. You can literally separate where you want to apply the data loss and where you want to apply the physics loss. And in this case, your neural network learns to approximate your data in the data region, but also learns to generalize quite well outside the data region, because at least it would be told to satisfy the physics where it has no data. And indeed, this is a quite powerful approach that I think more people should consider in physical systems.
Yeah, is make more safe to extrapolate out of your sampling space.
Yes, indeed, yeah. Any questions on that? Yeah.
I think if I understood well, in the classical definition, it starts with having loss function of the physical part with PD equations of the model.
Yeah.
But we find a lot of articles also that they don't use the PD part, but they use also another type of the physical equations that
yes,
do the PDs.
Exactly, very good point.
Let's say it started from PDs and it's extended to.
Yes, indeed, a very good point. Yeah, it's exactly as you said. So this field started with PDEs, so the motivation was to speed up the solution of partial differential equations, and that's fine. But then the field evolved. Okay, then people also working with real physical systems, because the seminal paper was only solving equations, no physical systems involved. There are no real world data. But then the people start saying, okay, wait, we have also the data. Why should I only use the physics loss? So I combined my loss function, my database loss function, where I have my physics real world data. And then I don't waste what the people said about physics informed neural networks. So I still combine data plus physics in the loss function, but exactly also not only when we have PDEs, yeah, also when we have ODEs or other types of equations, yeah. Yes, by the way, this can be ordinary differential equations, but it can also be any other equations you have, right? It can also be static equations, not differential equations, yeah. Right. Yeah, other questions? And my next question is if actually physics-informed loss functions can have different terms. So we learned they can have differential equations in their loss function, but can we also have other terms? Yeah, what we said now. And the answer is yes. You can have actually other terms. For example, in this case, the authors of this paper wanted to learn the inverse dynamics of a drone again, of a quadrotor. So they had, again, a pin, a physics-informed network, in which X, okay, it's a vanilla deep learning network, right? So nothing special. But they had, okay, X is the quadrotor state, Y hat is their control input. Okay, for example, in this case, it was the PWM command for their motors. And in the loss function, they didn't say they wanted to satisfy differential equations. They say we want to satisfy a different law, which is conservation of momentum. Okay, so conservation of momentum is another important law of physics, right, related to linear and angular momentum. So basically, in the absence of external forces, your momentum is constant, or external actions. And they wanted to conserve that, right? And they say, how can we do that? So the idea is exploit the correlation between your drone accelerations, especially the angular accelerations, and the motor command signals. So intuitively, they said, okay, our roll acceleration, so when the drone rolls about its longitudinal axis, the roll acceleration is correlated with the motor signal that we use to generate it. Okay, so when we want to roll, probably we need to have the right motors that spin differently from the left motors, right? And intuitively, there is a correlation, they say. And not only intuitively, they actually quantified the correlation, the coefficient of correlation, 0.67, whatever. So if you put the P dot, in this case is the roll rate here, and this is the PWM signal to generate it, you see there is a correlation, right? So when one is increasing, the other one is increasing as well. And same for pitch acceleration and its corresponding PWM signal. And also for the yaw acceleration, right? So when you spin on the vertical axis, here the correlation is even higher. You see, it's almost a line here. And so basically, they use this physical intuition and try to encode it in the loss. So how they actually did is they said, yes, intuitively we want them to exhibit the same pattern. Okay, so accelerations and PWM motor signals should exhibit the same pattern. They should be correlated. And they introduced this local monotonicity terms in their loss, LM term. So LM stands for local monotonicity. So they want it to be, the two signals should be related. And this is, again, soft constraints in their loss function for the roll, pitch, and yaw motion. And this is something they incorporated in the loss functions. In this case, we don't have equations, analytical equations, but we have these monotonicity terms that somehow explain this idea. And the first term is, of course, the standard data-based MSC term, right? So we have to minimize the deviations from our ground truth observations. Right? The thing is, okay, it works, but they also say if we have strong aerodynamic wind or effects, it may not be true that actually the yaw acceleration, for example, is so correlated with the motor commands. So if you have strong disturbances, wind, aero effects, also if it's not wind, but it's turbulence effects generated by the drone, it can be that this law is not true anymore, right? So this loss function term may actually be not always valid. Okay, depends on the data probably. And so what they said is, okay, we use that term, but sometimes we drive that term to zero. Okay, so we let the neural network learn the real aerodynamic effects. Okay, so that term, that local monotonicity term, can help sometimes. But if you see, this is the number of epochs, of training epochs. So one epoch is when the network sees the whole training data set. And sometimes, so like after 40 epochs, they are driving the lambda LM term, so the weight that multiplies the local monotonicity term. So basically the physics informed term. They drive this term sometimes to zero with a certain cyclical annealing scheduler. They call it like that. And this is an approach that maybe you don't see so often in the literature, but it can also be helpful. Like in this case, they were driving sometimes this term to zero, so that you have only the data loss, and then the neural network can learn if there are other effects that contradict your physics loss function, because it can happen, right? It's an assumption, but the assumption may be wrong. The assumption about physics may be wrong. So this is a way in which you can somehow circumvent that effect. Okay, it's again not so common in the literature, but can be done.
I want to say
Yeah.
that when at the beginning of the course we mentioned the idea that you can embed physics not only in the architecture, in the loss,
Yes.
in the input or the data set, you can embed the physics and physical intuition also in the training. And here's an example, no? Because you are not doing real standard training, but you had some prior intuition, some prior knowledge about your system. You know that this loss function may be not respecting all the case, and so you find a trick, an idea to improve the final result, including this information inside the training. So this is an example, simple example of including physics and ideas also in the training phase. Okay.
Yeah, indeed, yeah, good point. Yeah, this is indeed, it's not only in the loss function. So this category, this approach can be seen as a loss function based approach, but also as a training procedure based approach, because we want to manipulate, change the training process itself, using physics knowledge, basically. Right? Yeah. Questions here or discussions? Yeah. Yeah. Okay. So indeed, questions. Otherwise, I think we are at the end of this part. So this would conclude the physics informed part. And we can maybe start with the physics encoded part. Okay. Yeah, again, if you have questions, feel free. Otherwise, we can start with the third category of approaches, which is physics encoded architectures. Yeah. So far, we learned what are physics guided machine learning, what is physics informed loss functions. Now we have a look at physics encoded internal architectures. So yes, here the idea is also quite simple, at least in principle. And citing the survey paper by Farugi, he says basically physics encoded neural networks. He said textually we can call them like that when they forcibly encode non-physics into their core architecture. It's a very clear definition when they act on the architecture, then it's physics encoded. And here we actually have different classes. Okay, this is something we classify in this way. But okay, one can also find other classifications. We propose this one. So there are different ways to embed, to encode physics into the core architecture of machine learning models. And we're going to see briefly each of them. Or actually, today we're going to focus on the first two approaches. Then tomorrow, briefly on the third and fourth, and fifth probably also. And then we spend some more time on the model structured approach, which is an approach that Gaston and I, and also some PhD students here work a lot on. So we can start from the first approach, which is Lagrangian and Hamiltonian approaches, which sound complex, sometimes can be a bit complex, but in principle, the idea behind is very simple. So basically here, the motto, the slogan is learning dynamics from variational principles. So basically, with Lagrangian and Hamiltonian formulations, you can come up with some equations of motion of your system. And then the idea is to learn some parts of the equations of motion with neural networks. Okay, which parts we're going to see in a second. Okay, but the idea is in principle simple. And yeah, indeed. So there are different ways to formulate equations of motion in the literature, but you may have studied them since probably your high school, at least the most common approach, which is Newton formulation, of course. So, I mean, I think you all know the principles, but what's the idea of the Newton formulation? It's to say, okay, the sum of all forces is equal to the mass times acceleration. The sum of all moments, external moments, is equal to the moment of inertia times the angular acceleration. This is fine, but it means we need to write down free body diagrams. We need to write down forces, moments. We need to basically know a lot about the system, right? If you think of humanoid robots, maybe writing the equations with the Newton approach is not so easy, right? Because you have a lot of bodies, a lot of interactions, coupling, reaction forces. It can be a nightmare, yeah. Another approach is the Lagrange approach. I don't know how many of you have heard of that, at least. How many of you? Can you raise the hand? Okay, so maybe, almost all. Indeed, it's an alternative formulation for the Newton one, but it's different, because in this case it's energy based. We don't need to model directly the forces and moments. This is an advantage. We don't need to formulate to write down, sketch free body diagrams, whatever. And this can be more suited indeed for multi-body systems like robotics, robot arms, humanoids, or not only, but also systems with a lot of degrees of freedom that can be hard to model with Newton. So let's focus on the Lagrange approach for now. So here the idea is we have to model, okay, we don't have to model the forces, but we have to write the Lagrangian, okay, which is maybe another challenge. But the Lagrangian is typically defined as in terms of energy, so as the difference between the kinetic and the potential energy of the system. The kinetic energy, at least for some classes of systems, like rigid bodies, can be written in this way. 1/2 q and q dot are the generalized coordinates and velocities. So you can think of the angles of a robot arm, the degrees of freedom. Can be angles, can be velocities, can be whatever. We call them generalized coordinates. And q dot is their time derivative. M of q is the mass inertia, which appears here in the kinetic energy. Is the mass or inertia matrix, which appears in the kinetic energy. And it's a matrix in general, and it's symmetric and positive definite by definition. And G of Q, okay, the derivative of the potential energy with respect to Q is the collection of all the gravitational forces acting on the system, or all the conservative forces, more in general. And then from calculus of variation, okay, you can actually get to the famous Euler-Lagrange equations, which you probably have seen somewhere, which simply say that, okay, this is the Lagrangian. The equations of motion can be written like this. So the time derivative of the partial derivative of the Lagrangian with respect to q dot minus the partial derivative with respect to q is equal to tau. And tau is the vector of generalized forces and moments, non-conservative forces and moments. So like friction, like external forces, forces that really change the energy, the total energy of the system. Right? And then what can we do? We can substitute the expressions of the energies, kinetic and potential energies, in the Euler-Lagrange with these equations. And then we get to this formulation, which starts to resemble maybe something that you may know, at least for mechanical systems. This term, you can call it the C of QQ dots. And then you end up with something like this. So we have mass matrix times second derivative of Q plus this C term plus G plus the gravitational forces equal to tau. This is quite general. With this equation, you can express a lot of dynamical systems, at least mechanical systems, but you can generalize it also to other forms of systems.
Rigid body.
Yeah, rigid bodies. Yeah, exactly. Rigid body dynamics. Yeah, for sure. So M of Q again is the inertia mass or inertia matrix, symmetric, positive, definite. C is commonly called, it collects the centripetal and Coriolis effects that depend on Q and Q dots. G is the generalized gravitational terms, and tau is the non-conservative, generalized non-conservative actions. And yes, and now my question is, do we know all the quantities? Typically, maybe not, right? We need to estimate them or learn them, right? And what traditional engineering does, since 30, 40 years, is computing, actually, the mass matrix and the gravitational forces by hand, basically from measured or estimated masses, lengths, inertias. Totally fine, yeah. This is analytic, interpretable, limited complexity, but you need to measure things. You need to often not only measure, you need to estimate. Like moments of inertia are a mess to measure. You need to estimate them. With complex systems, it can be very tricky, typically. So vehicles, robots, estimating inertias is a well-known mess. On the other hand, deep learning says, who cares about the Lagrangian, right? We learn everything from data, and yes, and it can work. So you forget about the Lagrangian. It's flexible, no reliance on physics, on approximated models. But as we said, you need data, right? You need a lot of data, and then you can hope to generalize.
And of course, when you work on, if you think about ChatGPT was trained using thousands of gigabytes from internet, and was plenty of data to train that model.
Yes.
But here we are talking about robots, something that is working on real life, so it's not easy to get such much data to generalize. So I think in this moment it's not really usable and intelligent to completely forget all the physics now, because
Indeed.
you need to relearn what we learn, because 95% of the output of the system is known.
Yeah.
So from physics, no, maybe 5-10% is unknown, but starting from scratch to relearning everything, I mean, I don't think that is the
Exactly.
the right
If you
solution.
think, this is a very structured problem, yeah. So we have actually a quite general but still structured form to express the dynamics. So in this case, it can really make sense to say, okay, wait, we can still integrate physics knowledge without using traditional engineering, yeah. So having a mix of the two. And here there are a bunch of approaches. The first one I would like to start with is called deep Lagrangian networks, DLANs. They're also quite popular, especially in robotics. Yeah, here there is a paper from 2019. And here the idea is, okay, let's not forget about the Lagrangian. Let's keep the Lagrangian. And in particular, let's keep the structure of the Lagrangian and learn the mass matrix and the potential energy, or the vector G, with neural networks, with multilayer perceptrons in this case. So basically, you have your neural network that takes as input your generalized coordinates Q of the robot, for example, and that goes and estimates. So the output of the network is a mass matrix M and the potential energy V. So this is the Lagrangian, okay? T minus V, kinetic minus potential energy. Or equivalently, you can also learn G. I mean, the derivative of V is G, so you can also learn G directly. So we keep the structure of the Lagrangian, we don't forget. We just learn the hard terms. The mass matrix contains a lot of moments of inertia, very hard to estimate. Let's learn them with neural networks. Same thing for the potential energy. And now you may ask, why don't we learn also C? Because, I mean, this is another component, yeah? But if you remember the definition of C that we gave a couple of slides before, you can actually compute C as a function of the mass matrix and the generalized coordinates. So once you have an expression for M, you can simply plug it in here, you take the derivative, and you have C for free.
Sometimes you can use automatic differentiation. For example,
yes.
Here you can use automatic differentiation because you are deriving the output of the network that is M with respect to the input of the network that is Q. Not in all the case, because when you derive with respect to the full derivative, there you need to make discrete differentiation, of course.
Yeah, because this one would be the time derivative, but you can still rewrite it as partial derivative.
The cube of Q, and then
So this would be the time derivative, but then you can write it as the partial derivative with respect to Q
and the Q
times Q dot. Yeah. So yeah, but you can still use autodiff to compute that. So this is the idea. Yeah, very, very simple. I mean, learning two terms without throwing away everything. And then what happens? Okay, if we use a general purpose network, we are learning the mass matrix, but we're not considering that it needs to be symmetric and positive definite, right? So we may learn a matrix that is a full matrix, a dense matrix, and it's not symmetric and positive definite. Then the physics doesn't work anymore. So what they propose is, okay, let's consider these things, and let's learn, instead of a full matrix, we learn its Cholesky factorization. Simply means we learn two matrices. We learn actually another matrix, which is L here, and L is simply a lower triangular matrix, so full of zeros in the upper right block. And then M is simply given by the product of L and L transpose. In this way, you have a mass matrix that is symmetric and positive definite for free. You don't need to impose anything else. And you just learn L. So you have also a lower amount of parameters to be learned. okay? And all the rest remains like that. And how do we learn actually M and G, right? Because, okay, we want to learn them, but how? Well, we can simply learn them with supervised learning. So we take the predicted generalized forces and moments tau. So we just take the equations of motion with the learned M and G. So these are neural networks, M and G. We compute tau from the equation. But then we also have the measured tau, okay? So we also have the measured actions applied to the robot, because maybe we have collected some data with the robot. And so in this way, we can simply have that the loss function is tau minus tau hat, right? The norm square of tau minus tau hat. And so this is supervised learning. We're not changing the loss function. This is a data-based loss function. But we are acting on the architecture, if you want, of the network. Because then you can see, if you want, you can see everything as a big neural network with some components that are actually neural networks and some others that are physics equations. And you're also acting on the structure of M. You're saying M is not a general purpose network. It's actually the product of two lower triangular matrices. So I think you can agree that we are actually putting some biases, some inductive biases inside the architecture in this case. Right? Questions here? If not, okay, this is the theory. This would be an example, for example, of deep Lagrangian networks. In this case, so from the same authors. In this case, they wanted to control the inverse dynamics of a robot, of a 7 degree of freedom manipulator, for example. So they wanted to perform trajectory tracking. Okay, so they had some desired joint positions, velocities, and accelerations. So some time trajectories to be tracked by the system. And they wanted to perform this task using, at the end, deep Lagrangian networks. So their idea was to say, okay, traditionally, to perform this task, you simply use a PD controller, okay, a simple proportional derivative controller. So you have your tau, which is the motor torques at the joints. So the robot can have one motor at each joint, for each joint. And very simply, traditionally, you can have your tau t is given by PD controller. So proportional controller that multiplies desired reference minus real position q plus derivative controller, okay? We take the target derivative. That works, but they said, okay, let's add a feed-forward term. So let's do feedback plus feed-forward control. And the feed-forward term was actually computed using the dynamic equation where M and Q are learned. They are neural networks. And this works. So yeah, this is the block diagram. So you see they had here the inverse model. So f to the -1 means actually this equation. So they compute, this is tau feed-forward. And then they had the PD controller to compute the feedback term. And then they fed the control to the robot. Okay, so then they were controlling the real robot in real life. They were actually doing some online learning here as well. So they were refining then M and G with the collected data as the robot was going somehow. So yeah, and they showed the approach was quite effective. They were outperforming a general purpose feed-forward model. So there you see the training, the training function. So basically, the proposed approach was having a lower loss in this case, and it was also generalizing better to new data. Yes.
What about having approximated mass matrix and gravitational vector? Did they also compare with this case or not?
So with the purely physics-based, I don't remember if they did in this paper, probably not, but there are, I think, some papers that do it. Because of course, yeah, the challenge is, especially with this type of robots, is estimating the inertias. Yeah, the masses you can know, but the inertias are a bit more tricky. And also the
interesting what you said, because
Yeah.
you know exactly, because in theory, in principle, no, G and M are known. Yeah. So yeah, in principle, you can just replace
Yes.
with a standard computer
Yes,
torque.
yes. I mean, you're right, and this can be done. The thing is, with a neural network, you're both, if you want, you're both learning M and G, but implicitly you're also saying, okay, this equation is generalized. Like this equation is not the one I would have with the pure Lagrange approach, but I have a neural network, so I have more flexibility.
Yeah,
So-
probably are learning something.
Yes, exactly. You're learning something else, yeah, on top of the mass, probably.
Yeah.
You're learning the mass plus some corrections to make the model work well. Yeah, this is the power implicitly, right? Even if at the end you're learning a matrix, but you have a neural network, so a lot more nonlinearity inside, and this gives you more power. Yeah.
And another question, did they also, so the validation part was on the learned data or on unseen data?
Also on unseen data, I think in this case. So, okay, this is the training loss function, but then they are also showing that they have better generalization to new
Okay,
data. And also in other papers, they actually show that they have
okay.
Of course,
better
with respect to the
generalization.
logarithmic network is
Yeah.
something that you can
Yeah.
suppose
Yeah.
to be.
Understandable.
I mean, of course, you have no guarantee that you generalize better than a physics-based model. You have maybe
Based, yeah.
yes, because yeah, with physics models, it's hard to mess up stuff, yeah. But in this case, you have neural networks, so nobody can guarantee that they will generalize well outside of the training domain. But the real power would be what we said before, maybe combine this with also a physics-informed loss function outside of your training set. That would be maybe more powerful in this case, yeah. If you really want to be sure that you generalize well outside the training set.
I think that could be interesting to compare the real mass matrix to the
Yes.
learned one in order to see if the MLP, because there are MLP,
Yes,
are learning something that is not related to the mass matrix.
Exactly.
But, and of course, it's doing it. I think.
of course, yeah, of course, yes. I mean, it's still preserving at least the symmetry and the positive
Yes.
definiteness, but I'm quite sure if you compare the ground truth mass matrix that you obtain, it should be different, yeah, at least, yeah, from the. I'm not sure how much difference it would be, but it depends, because this equation is still a model, right? Where's the point?
Yes.
This equation is still a model, so the models are imperfect by definition. So it's normal that you get something else, yeah, that is not purely physical. But that's also what we want to have, right? We want to enhance the flexibility because models are imperfect, yeah. Yeah. Okay. And
Yeah, also
Yeah.
the other things that you can do here will be some example that you will see in the next part of the presentation to add some residual network.
yes,
To learning maybe what is not inside. Also, probably including some residual, you can also help to the network to learn more close to the real dynamics, avoiding to modify those metrics, including some effect that are not comes from the inertia and the gravity, no? So if you add an additional residual, as we will see in the next part of the presentation as another approach, you can improve both the learning of those network and the residual, so you can
Exactly. Yeah. So,
decouple the
yeah,
effects.
there are different approaches
Yeah.
to do better than this. Yeah, one would be physics-informed loss function. On top of that, the other one would be add a residual. So here we can add maybe another residual correction that can be another neural network, or different things that can be done. Yes. So yeah, if there's no other question, maybe we can take another short break if you want, or do you prefer to close before? We can also close before, yeah, because then we need to skip the line and the Mensa, yeah. Yeah, okay, we can continue. It's fine for you. So yes, we've seen the Lagrangian once before. There's another approach that is called Lagrangian, not deep Lagrangian, but only Lagrangian neural networks. That is strongly related to the deep Lagrangian, but there are differences. So in this case, in the case before, we had a structure on the Lagrangian, okay? We said Lagrangian is, or I mean, the final equations we have a certain structure, like mass matrix times second derivative of Q plus Coriolis plus gravitational. This is true, but it's true. So this structure of the Lagrangian is true for rigid body systems, yeah, for rigid body robots, vehicles, other systems. But if you have charged particles, electrical systems, whatever, then this is not the Lagrangian anymore. Like this function here, you don't have maybe a mass matrix, or I mean, you express the kinetic energy in a different way. So you can still have kinetic minus potential energy, but the expression of the kinetic energy maybe changes, and also for the potential. So the Lagrangian approach is different. Lagrangian neural networks say we want to be more generic. We don't want to use this equation that was used by deep Lagrangian. Here we want to learn the whole Lagrangian directly from data. So we have measurements, QQ dots, learn everything from data.
We reduce the structure.
Yes, it's a step back, yeah, but it doesn't mean it's worse. I mean, it's a step back because you can apply it to different systems. Yeah, deep Lagrangians are only for robotics at the end. Yeah, so in this case, it's more general. Yeah, it's more general for the Lagrangian structure. And still we aim to preserve energy conservation, which is an important principle that with a traditional neural network you cannot enforce. And so what's the idea here? Yeah, the idea is to learn the Lagrangian from data, but then how do we encode physics then? We can still use the Euler-Lagrange equations, right? So L is learned with a neural network. But we don't forget the Euler-Lagrange. Okay, so if you then use the chain rule to expand this term, so it's the partial derivative with respect to time. I mean, it's the total derivative with respect to time. But the Lagrangian is actually a function of QQ dot. Okay, so you can expand it. This would be so you expand this one as the derivative with respect to Q, or the gradient with respect to Q of nabla Q dot L, okay, times the derivative of Q with respect to time, so times Q dot. And this is the second term, so this is a partial derivative with respect to Q dot, so nabla Q dot, times the original term, times the derivative of Q dot with respect to time, so Q2 dot, right? So it's simply applying the chain rule to expand this term here, right? This is the term with respect to Q. This is the derivative with respect to Q dot. Nothing strange, right? And from here, we can write that Q dot is a function of the Lagrangian. So we can express Q dot as a function of the Lagrangian, its gradients, Q and Q dot, okay? And again, L here is a neural network. But Q dot is computed in this way, which is a physics-based way. And the loss function can be on q dot in this case. So maybe you measure your accelerations, q dot, your system acceleration, and then you have the predicted acceleration, and you minimize the deviation.
Here is use the automatic differentiation.
Yes. So to compute these gradients, nabla q dot, nabla q of a neural network, we use typically autodiff, automatic differentiation, to make the process more effective. Yeah. So yes, here the idea is we use the first equation to compute q dot. And then we have our Lagrangian neural network, our neural network in general, that takes q and q dot as inputs and computes the Lagrangian L. But then we take the gradients of the Lagrangian with the autodiff, and we use the gradients to compute q dot, q2 dot, so the acceleration from the Euler-Lagrange equation. Right, so we have here we have a very general purpose network, can be an MLP, multilayer perceptron, to relate q and q dot with the Lagrangian, but then we plug the Lagrangian inside the Euler-Lagrange, and we solve q2 dots. We compute q2 dots. Right? Yeah. And the thing is, by doing so, we can show that general purpose networks lose energy over time, while this construct, Lagrangian neural networks, LNNs, conserve energy. So this is an example with a double pendulum. Okay, these are the equations of a double pendulum. We can observe the state over time, so as the pendulum moves over time. And we can use a baseline neural network, a vanilla neural network, that relates q and q dots with q2 dots with a neural network. So no Lagrangian here. And the authors have shown that this network, if you use it and integrate q2 dot over time, over long time horizons, then you tend to lose energy. And we will see that in the next slide. While if you use the Lagrangian, so observe the state over time, observe q and q dots over time, use the Lagrangian, use the neural network to compute Lagrangian and then Euler-Lagrange, then you can conserve energy over time. I mean, at least you lose less energy, let's say, over time. And this is what they show here. So this is a double pendulum, frictionless double pendulum, so no frictions. Energy should remain constant forever. Total energy, mechanical and potential. But what happens with a baseline neural network, you actually lose energy over time, especially when you integrate over a lot of seconds, yeah, 1000 seconds. So you lose energy with the baseline, while the Lagrangian loses way less energy. And here you see also the comparison of the θ1 and only θ1 coordinate of the double pendulum, so one of the two angles. At the beginning, everything works fine. Yeah? If you integrate for 10 seconds, the baseline is perfect. But if you integrate for 150 seconds, then you see the deviations. The baseline goes out of phase. It's not predicting well anymore. This is the error, an error of more than 1 radian, probably. So it's a lot. You go completely out of phase. You lose a lot of energy. That's not what we want. Yeah. Questions?
The reason why this happened is because when if you go back one, when you create a network like this, no, you estimate. I don't remember if in this training they perform also the training in loop or not for this one. Do you remember?
So the loss function should be on Q2 dot here.
And just the QQ dot.
Yeah, so probably
Double dot,
they
yeah.
integrate on a long time horizon, yes.
But we not make the loss on the integrated.
Okay, no, probably the ground truth states, I think, is QQ dot are the ground truth in the
And
loss
that-
function.
yeah,
Yeah,
that's
should be
it,
the ground
okay.
truth, yes.
But the problem is commonly, here it showed that was losing energy. I'm not really sure that can happen also the opposite. Because if you train just on Q double dot, I mean, there is no reason why you not learn a little bit more acceleration that, because if you are just training on the single Q double dot, maybe you learn a little bit
You
more
may also
energy,
gain energy
you-
probably.
you, diverge. I know for sure that if you train, instead if you take a double dot and you integrate the double dot, you obtain a Q dot. And also you integrate again and you obtain Q. And then you train also using that loss. So using a loss on Q dot and Q. What happened for sure is that you lose energy. Okay, because it's more probable.
Yeah, no, but maybe, okay, no, maybe they do it in that way then,
Yeah.
yes.
Because otherwise it's impossible to say that is not diverging. No, because maybe
I mean,
you
here,
learn that you are.
so at inference time, I'm not sure what they do at training time, but at inference time, they are integrating in closed loop, yeah? Yes.
Yeah.
So they just use a Q2 dot, they integrate it over and over again. And in this case, the system is unforced, so there's no external action.
Yeah.
So you can only lose energy.
Use energy.
Yes. Or you keep it constant in the best case, yeah. Yes. Okay. Okay, we can see maybe last thing for today, yeah, then we close, which is Hamiltonian. Hamiltonian, okay, it's not Lewis Hamilton from Formula One, but it's another approach to express the equations of motion of a system. So before we said, yeah, we have Newton and Lagrange. This is not completely true. We also have Hamilton. We also have Hamiltonian formulation. It's less known, I think. Here, very few of you know the Hamiltonian because it's indeed it's used for very particular classes of systems, typically. It's still an energy-based approach, very related to the Lagrangian, but it's typically used for systems with many degrees of freedom, like quantum, celestial mechanics, or fluid dynamics, or systems with really a lot of degrees of freedom. I mean, in principle, you can apply it to every system, but there is a reason. We're going to see why. It's not so popular for other types. But still, this approach is still applied also in robotics. Yeah, so pay attention. It's not something that if you do quantum, I mean, you should only use if you do quantum. Yeah, I mean, you can also use it in a lot of other types of systems. So yeah, here we have we don't have the Lagrangian anymore. We have the Hamiltonian. The Hamiltonian is something. It's another function closely related to the Lagrangian. There is this Legendre transformation to relate the two. So if you have the Lagrangian L, you can compute the Hamiltonian H in this way with this relation, the Legendre transformation. L was depending on Q and Q dot. H is actually depending on Q and P. And P, so Q is always the generalized coordinates, but P is something we call momentum. Okay, so the P variables are the momenta, they're called. And the momentum is something a bit more tricky. So if you think of a particle or of a system, the momentum can be the linear momentum, okay, or angular momentum. But what if we don't have a system that moves, or if we have an electrical system, what is the momentum? There it's a bit more tricky. I mean, you have to come up with your own formulation of the momentum. But that's fine. I mean, that's another way to express the equations. And then plug the Hamiltonian in the Euler-Lagrange, you obtain something like this. So this was the Euler-Lagrange with the Lagrangian. And this is the so-called Hamiltonian equations of motion. let's say that the time derivative of Q is equal to the partial derivative of H with the P, and vice versa for P with a minus sign here. And tau is always the generalized external actions. So in the autonomous conservative case with no external actions, these are the equations, right? These are the equations for the case in which you have no external force. So the equations are actually quite simple, but formulating the Hamiltonian can be a bit tricky. Indeed. So in many cases, the Hamiltonian is designed to be equal to the total energy of the system. So this means the sum of the kinetic and potential energy. So in the case of the Lagrangian, we had a minus sign here. In the case of the Hamiltonian, we have a plus sign. It's a design choice. In some cases, we can design it like that. But indeed, it's a design choice. And expressing the momenta is particularly tricky for some classes of systems. So this requires domain knowledge, can be very tricky. So what's the idea of Hamiltonian neural networks? Let's learn the Hamiltonian from data, so that we don't need to design it. Learn it from data and still preferably conserve energy. So related to the Lagrangian approach still. Yeah, so we want to learn H from data with a neural network. So we parameterize H with H theta, yeah, with our neural network with some parameters theta. And the goal is to satisfy the Hamiltonian equations. The Hamiltonian equations are these, yeah? So do you have any ideas how we can learn a neural network while satisfying these equations? Any idea that comes to your mind? Based on maybe what we've seen this morning. Yeah. What we could do is to act on the loss function, yeah, because we have basically data. Okay, the data can help us learn the Hamiltonian, but we want to do it by satisfying these equations, and so we can act on the loss function. So in the loss function, we can say, please minimize the deviations of or the violations of the Hamiltonian equations. Okay, with the we're just using dp dt, but it simply means q dot and p dot. Yeah. So basically, in the loss function, we want to minimize the violation of the Hamiltonian equations because they are very simple. Yeah. So it's a pity not to use it in the loss function. And so we have a neural network that learns the Hamiltonian from Q and P. So again, Q is the generalized coordinates, P is this momentum. This is a neural network, general purpose one. And then the problem is in the loss function we need the HDP. Okay, we do not need H directly, so we need to compute the HDP and the HDQ. And to do that, we can use autodiff again. So we take the output of the network, we differentiate with respect to Q and P with autodiff. We have it quite easily, yeah, let's say, with automatic differentiation. And then we need also Q dot and P dot.
Yeah, these are a bit more tricky.
Yes. Q and P dot, we can compute it. So typically in the data set, we have Q and P. So we can compute Q dot P dot numerically with the numerical derivatives. Or if you have it analytical, you can compute analytically or whatever, yeah, your choice. But then we have the loss function in this way. Okay. So the loss function that satisfies the Hamiltonian equations. And yes, indeed, in the training, we want to minimize the deviations of the HDP and the HDQ with respect to Q dot and P dot. And again, similarly to what we said before, general purpose networks can lose energy over time. The Hamiltonians can conserve energy. Here it's another example with an ideal mass spring system without frictions. So it should conserve energy. We observe, we have some noisy observations of Q and P. So in this case, the Q is the physical quantity, okay? The elongation, the position of the mass. P is the linear momentum, so mass times velocity, linear momentum. You have your observations. You can use the observations to train a baseline general purpose network, a baseline network from Q and P. It learns Q dot P dot, and then you integrate Q dot P dot over time, and you lose energy, basically. You tend to lose energy. You can lose energy if the training goes badly. Instead, with a Hamiltonian, yeah, you take your noisy measurements, Q and P, you use them to train your neural network for the Hamiltonian, and then you use the Hamiltonian to basically train your model in the training function with the loss function we've seen before. And at the end, if you integrate the Hamiltonian, you tend to conserve better the energy, similarly to Lagrangian. Yeah, so these are some numerical results you see for the ideal mass spring system. And you see, yes, with a baseline neural network, the phase portrait tends to go towards the origin. You tend to have more deviation between your ground truth coordinates and the predicted ones. And you tend to lose energy again, or still change the energy of the system. Total energy, yeah, goes down for the baseline neural network, while for the Lagrangian, it's closer to the real system. Of course, here we're integrating on 20 time steps. If you go more to the future, you should see even more difference. Yeah. And this is for a frictionless pendulum, same idea as before. You lose energy and you tend to have better predictions with the Hamiltonian approach. And then last thing for today is, can we learn, so here we learned the Hamiltonian from coordinates, yeah, from the coordinates of the pendulum or coordinates of a spring or whatever. But what if we have only images as input, yeah? So maybe our robot, whatever, has a camera, we see the images, and we want to learn the Hamiltonian from pixels, pixel observations. In this way, well, some authors propose to start from an RGB image, for example, of the pendulum that moves. And then they were using an autoencoder, or let's say an encoder. So this is a neural network again here, for example, a variational autoencoder that takes the image, compresses the image in a latent space. Yeah, we call it latent space because it's a compressed representation. So the image can be a high resolution image, but it's too much, yeah, too much information. We compress it in a latent space. So ideally only the information we need about the image. And then we use this latent space. We interpret the latent space as Q and P coordinates. And then we feed that to the Hamiltonian neural network. So instead of training on position and momentum P, we train on the latent representation of the input image. And it works. Yeah, I mean, they showed actually they could approximate quite well the evolution of the pendulum over time. This is also the pictures. Yeah, so ground truth and Hamiltonian are aligned. The baseline tends to lose energy at the end. So the pendulum does not move anymore at the end. Okay. Yeah, questions? So this approach is, of course, more general. Yeah, we've shown it with the two simple examples, pendulum and mass spring damper, mass spring, sorry, but it's been applied to more complex systems. But this is just to show you the intuition behind. Okay, so yeah, if there's no question, we can also close it for today and we continue tomorrow. Yeah, always in this room.
See.
Yes, always in this room, yeah. Apart from Friday, which we are again in the seminar room. Yes, and if you have questions, whatever, just